In this lesson, we're going to take a look at dimensional analysis. Now, I know that when we think dimensions, we're thinking, what are we actually measuring? Well, dimensional analysis allows us to see if what we have derived is actually valid in terms of its dimensions. So, there's an equation, say, that says the displacement of an object is equal to 1/2 the acceleration times time squared plus the initial velocity of the object times time, and that equation, there's no guarantee that it's correct until we've done that, but we can check to see if it makes sense dimensionally. And what I mean by that is, in order for us to add two quantities together, remember they have to be in the same dimension, and if I want to say two things are equal, they have to have the same dimension. So I could say delta x, that's a change in position. Position is a distance from a reference point, so this has got a unit of a meter. This is a number. I don't care what its units are. It doesn't have any. I don't care about its value, so I don't worry about it. Acceleration describes the rate of change of the rate of change of velocity. It's measured in meters per second per second. Time is measured in seconds, but that doesn't say time. It says time squared. So I have seconds squared, and then I have velocity again, which is still got, whoops, that should be brackets, still got a unit of meters per second. And then I have times time, still has a unit of seconds. Now, if I look at the dimensions, that's what I've done here. I've pulled out their units. Then I can see that this is just meters. There's nothing going on over there, which means the right side has to be meters. And so this second cancels that second. This other second cancels that other second. So I have the dimension of meters is equal to the unit of the dimension of meters plus the dimension of, and that second cancels that second. And I do see that I have meters is equal to meters plus meters. Remember, it's not about how many are on each side. It's about whether or not the dimensions match. And since a meter plus a meter is still going to be a meter, I have the dimensions on the left are equal to the dimensions on the right, and I can add all of those up. Now, I can ask this a different way, and I can say, well, what unit would a term in an equation have if it's going to be dimensionally correct? So let's say I have the equation, the force due to gravity is equal to m1 times m2 times g divided by r squared, where force is, or F is force measured in newtons, and m is mass measured in kilograms, and m is mass measured in kilograms, and r is a distance measured in meters, but that says r squared, so that's got to be meters squared. What are the dimensions of g to make this equation work? Well, that means I want to isolate the dimensions of g. So I'm just going to put g in my bracket. I'm going to rewrite all that, and I have the dimension of Newton is equal to kilograms times kilograms, which is kilograms squared, divided by meters squared times the dimensions of g. And if I divide both sides by kilograms squared and I multiply both sides by meters squared, right? So I'm going to multiply meters squared divide by kilograms squared. So those units go away. I'm just treating them as algebraic quantities. I can do that over here as well. I have to. Meters squared, kilograms squared. Then I can see that my dimensions of g are Newton meters squared per kilogram squared. But I should take that a step further, because a Newton is a derived unit that is equal to a kilogram meter per second squared. And now I'm going to multiply that by meters squared and divide it by kilograms squared. I dropped my brackets, but they're all still there. So that square cancels that kilogram, and I'm going to end up with meters cubed. So I have meters cubed per second squared kilogram, and there's my final dimension of the universal gravitational constant g. So it's just a matter of treating the units as algebraic quantities to see if, one, we follow all the rules. Can we add meters to meters? Sure. And two, what should the dimensions of this constant be, so we can make sure our equation makes sense.